So we've got this far, and now what we're going to do is we're going to create this interval, this buffer zone around this. And the formula is this. It is p hat plus or minus. And then what we have here is I'm going to change this. Instead of, well, no, we'll just do it. It's 1.96 times the square root of p hat times 1 minus p hat over n. Okay? Now, why is it 1.96? Because that's how many standard deviations we need to go for 95%, except for we're going to use standard error. So here, let's fill in some numbers. So this is 0.14. 0.14 plus or minus 1.96, just filling in, square root of 0.14. 1 minus 0.14 is going to be 0.86, I'll put parentheses there, divided by the sample size of 20. Okay? So when we figure this out, look, I've got a calculator here. Didn't really want to use this one, but that's what I'll do. All right? And I'm going to do this part first. So I would do 1.9.8, and then where's square root? I don't know this calculator. This makes me look like I'm a bad teacher, but you know what? I don't care. All right, so I would have 0.14 plus or minus 1.96. I'm going to find the value for the standard error, and this is 0.0776. Okay, and then I'm going to multiply that by 1.96 times 1.96, and I get that this is 0.152. And I'm going to take it one decimal place more than this. Okay, that's how I'm going to treat it. I'm going to treat it as one decimal place more than that, just to make life a little bit easier here. So what I have here is 0.14, and I got plus or minus 0.152. So what does that mean? That means that I'm going to go 0.152 in this direction. I'm going to go 0.152 in this direction. So if I go to the right 0.152, that's going to put me at 0.292, which would be like there. So I got here, this is 0.292. If I go the other direction, I'm actually at negative 1.2 down here. And that's my buffer zone right there. So I created this area called a confidence interval, and I'm going to sit there and say, you know what? I'm pretty sure it's going to be in that range. That's what my goal is to say here. Now, let's put some terminology into this, because there is some things that need to be said here. Okay? All right. This is what we say. We say, we are, and it helps if you do it like you're from Monty Python. You go, we are 95% confident that the true proportion, and what we should do is we should put this in context, the true proportion of people who scored below 1,000 is between, and then we would have negative 0.12 and negative 0.012 and 0.292. We are 95% confident that the true proportion of people who scored below 1,000, and I'll put that there like the caret, is between negative 0.012 and 2.92. Now, that's not a probability statement. And the reason it's not a probability statement is because we don't have the population value, so we can't make that statement. All we can do is say, we're pretty sure, but we say it like this. We are 95% confident that. And then we fill this out. Now, here's my tricks that I want to incorporate here. Okay? And we'll talk about this in a second. When you're doing these problems, what makes life a lot easier is this. If you define n, p hat, and p, it makes life a lot easier. As in, n is your sample size. Well, I've got 20. 20 what? I've got 20 people. Okay? P hat. What is P hat? P hat is, okay, it is the 14, that's not the 14 out of 20. Well, I had 0.14. I don't know what that value is. Okay? It's the 0.14, which isn't going to work out well. But anyhow, it's the 0.14 of people who, and then talk about what it is, because you understand what this is. P hat is the people who scored under 1,000. If I can define this in the context of the question, then this becomes easy, because P is, it's the same definition here of people who scored under 1,000, but it is the proportion of the population as opposed to the proportion of your sample, because this is the proportion of your sample. It's the proportion of the population, then it's the same thing, of people who scored under 1,000, of people who scored under 1,000. So by defining N, it helps you to define P hat. And if you have P hat, you can define P. Why do I need to define P? Because when you give this statement, we are 95% confident that the true proportion, this is from here, this true proportion of people who scored below 1,000, that's your definition of P, and then you have to give your values. Okay, what else do we need here? We need some definitional terms here, okay? This, which is our formula, P hat plus or minus, when it was 1.96 times the square root of P hat times 1 minus P hat over N. Is this always going to be 1.96? And the answer is no. That is going to be what we've got two values for it. Okay, we can call it Z star because it's based off of the Z table. But sometimes they call it Z star. It's also called your critical value. How many standard deviations, we're in this situation, how many standard errors it is that you want to move. And this varies depending on the percent that you want. What percent do you want? And the typical are 90%, 95%, and 99% confidence level. How confident do you want to be? Do you want to be 90%, 95%, 99%? 95% is the default. Like when you open up Word, Courier is the default font. This is the default for confidence intervals. So this is 1.96. However, you have different values depending on the confidence that you want. If you want a 90% confidence interval, that Z star critical value is 1.645. Meaning, if I've got a normal curve here, and I go 1.645 standard deviation to the right, and negative 1.645 standard deviation this way, 90% of all data lies within that range. 95%. If I go 1.96 to the right, negative 1.96 to the left, or 1.96 to the left to negative 1.96, 95% lie within that range. 99%, which you can't see because it's down here below here, and this thing stinks, okay? 99% is 2.58. So, our critical values here for 90%, the critical value for a 90% confidence interval is 1.645. You will have to know this value. For a 95% confidence interval, your critical value is 1.96. For a 99% confidence interval, we will use 2.58. You have to know at least these two. This one's kind of like a bonus, but you have to know these two right here because these are the two big ones right here. If they give you something else, you either have to find it, we'll discuss that in class, or you will have to, or they'll give you, the critical value for that, or they'll ask you to discover it algebraically. All right, so looking again, P hat plus or minus, and then I'm going to call this Z star times the square root of P hat times 1 minus P hat over N. Okay, so this is the critical value. This entire thing right here, this entire thing, that value that you add and subtract from this is called your margin of error. And that's big. Margin of error, big name. When you see information about that they report about percentages, proportions in the news, and they sit there and say, oh, we feel that this politician has this percent of the vote. Like, you know, like previously they were saying, oh, Obama has like 54% of the vote. And then they'll say this, they'll say with a margin of error of 3%. And what that means, or they'll say a margin of error of 0.03, which is 3%. That means that this distance that they're going to say, they're confident, this is their sample size, but it could be anywhere between 0.57 and 0.51, because that's what their confidence interval is, based off of their sample size and based off of their sample proportion, or p-hat, and their sample size. And that sample size, when they do those polls, typically somewhere around 1,000. That's their margin of error right here, okay? So this entire thing is your margin of error. You've got your z-star, and of course, this is your standard error. All right. I think that's going to be it for chapter 19. Let's walk over here real quick, flip the page. No, that's all I want to talk about. All right. Super groovy.